A sharp whine tears through the humid air of the Atlantic Ocean, spinning so fast that the human ear can barely track its trajectory before impact. It is not the dull sound of a common cannonball crushing the wooden hull, but rather the terrible noise of iron chains whipping the wind like a propeller of death. When this bizarre projectile hits the target, it does not seek to sink the enemy ship, but rather to leave it sterile, powerless, and adrift. Two spheres of solid iron, connected by 30 centimeters of thick links, spin around an unstable center of gravity, transforming into a flying circular saw capable of decapitating oak masts with the same ease as a scythe cuts dry wheat in autumn. The British Royal Navy did not commission these ballistic abominations to pierce the lower deck, but to destroy the complex web of ropes and sails that gave life to French frigates. Imagine the panic on board when a single successful shot spinning at hundreds of kilometers per hour collides with the main mast. The wood explodes into splinters the size of daggers, the hemp rigging cracks like a whip, and within seconds, tons of sails and spars crash down upon the crew, trapping men beneath heavy canvas while the ship loses all maneuverability. It was a war of immobilization, where the goal was to turn the opponent into a static target for subsequent slaughter. For this choreographed destruction to function at sea, the engineering behind the object needed to be perfect, as a manufacturing failure would result in the death of the very crew firing the cannon. If the chain broke inside the barrel during the ignition of the powder, the two balls would fly off in random directions, destroying the mouth of the cannon and shattering the English gunners. The manufacturing of this piece required a dangerous fusion of two distinct metallurgical techniques, a forced marriage between brittle cast iron and flexible wrought iron, something that challenged the limits of mid-18th century foundries. But the design on paper does not sink ships. It takes iron and fire to make it real. If you value this kind of technical and visceral story, leave your mark by subscribing to the channel. Now protect your eyes, for we are about to open the furnace door. To understand where this weapon was born, you need to forget the modern idea of an organized factory and visualize an artificial cave of blackened bricks, where the only light comes from the gaping mouths of the reverberatory furnaces. We are in the industrial heart of pre-revolution England, perhaps in Woolwich or the foundries of Sussex, where the air is so thick with mineral coal dust and sulfur fumes that the workers' lungs wheeze like punctured bellows with every breath. The heat here is not just uncomfortable, it is an oppressive physical presence that cooks the skin and dehydrates the human body in a matter of hours, requiring men to drink liters of weak beer just to replenish sweat and remain standing. The ground is a treacherous mix of beaten earth, black molding sand, and iron filings, where walking barefoot or in worn shoes meant inviting tetanus and third-degree burns. Gigantic piles of scrap iron, old cracked cannons, and pig iron bars await to be fed into the furnaces, loaded onto the hunched backs of apprentices who rarely lived beyond 30 years of age. The noise is deafening, a cacophony of hammers, the constant roar of burning fossil fuel, and the shouts of the foundry masters coordinating the frantic rhythm of production, for war was on the horizon and the Crown demanded tons of ammunition. In this hostile environment, chemical precision was a gamble based on intuition and the color of the flame, not on measuring instruments. The master foundryman needed to know exactly when the iron reached the perfect liquefaction point, watching the blinding white glow of the molten metal. If the iron was too cold, it would clog the complex molds of the chain. If it was too hot or had too much carbon, the balls would become brittle as glass. All this took place under a low wooden and tile ceiling, where oily soot accumulated in stalactites, ready to fall and ignite at the slightest contact with a lost spark, creating a scenario where the risk of death was part of the daily work contract. Before any liquid metal could be poured, the most critical part of the process needed to be done entirely by hand, away from the melting furnaces in the forging section. The cast iron used for the balls is excellent at resisting compression but terrible under tension. If you made the chain from cast iron, it would shatter on the first impact. Therefore, the chain needed to be made of wrought iron, a fibrous and malleable material, laboriously worked by blacksmiths who hammered red-hot bars of metal on massive anvils until the impurities were expelled and the metal grains aligned to withstand violent pulls. Each link in this chain was a matter of life and death. The blacksmiths heated the bar to a bright orange, folded it into a U shape, intertwined it with the previous link, and then hammered the ends together in a fusion weld, where the metal fuses under pressure and extreme heat. There could be no failures, air bubbles, or cold welds. A weak chain meant that, when fired, the centrifugal force would separate the balls in the air, nullifying the cutting effect and wasting the precious gunpowder of the king. Thousands of these links were produced each week at a brutal pace that left the blacksmith's arms swollen and their hands permanently calloused and burned. The technical detail that separated mediocre ammunition from lethal was in the ends of the chain. The blacksmiths could not simply leave the last link smooth. They needed to create an anchor, often bending the metal into irregular shapes or creating mushroom heads on the tips that would be hidden inside the balls. This was essential because the cast iron of the spheres needed to physically grip the wrought iron of the chain. If this interface failed, the ball would fly alone, leaving the chain behind. With the chains ready and stacked like cold metal snakes on the workshop floor, the most dangerous stage was about to begin. Encapsulating these cold tips in a bath of liquid iron without causing a thermal explosion. Away from the rhythmic noise of the hammers, in a quieter and damper corner of the foundry, worked the molders, men whose patience contrasted with the violence of the product they created. The process began with sturdy wooden boxes called flasks, which were filled with a special mixture of green sand, not for the color, but for the moisture, clay, and charcoal dust. This sand needed to be fine enough to copy the details of the sphere, but porous enough to allow explosive gases to escape when the liquid iron invaded the space. The artisans pressed halves of wooden models into the compacted sand, creating two perfect hemispherical cavities that, when joined, would form the negative ghost of cannonballs. The logistical challenge for chain shooting was geometrically complex, as it was not just a matter of making two separate balls, but of connecting them indissolubly through the void. Between the two spherical cavities in the sand mold, the molders manually dug a small channel, or bridge, where the wrought iron chain would be carefully laid. It was delicate surgery done in the black earth. The chain needed to be perfectly centered. If it was crooked, the center of gravity of the projectile would be misaligned, causing the ammunition to spin erratically and miss the target by hundreds of meters, or worse, hit the sides of the cannon as it exited. Once the chain was positioned, with its anchoring ends projecting into the spherical voids, the top of the sandbox was closed and locked with heavy iron clamps. What remained inside was a buried secret, a skeleton of cold wrought iron waiting to be covered with flesh of molten iron. The precision here was visual and tactile. A loose grain of sand could create a flaw in the surface of the ball, and any excess moisture in the clay mixture would turn the mold into a steam bomb as soon as the incandescent metal touched the damp interior. The moment of the pouring was the peak of tension in the foundry, the instant when chemistry and physics entered into a violent conflict. Two strong men carried a foundry pot suspended by a long double shaft, transporting 30 or 40 kilograms of molten iron glowing at more than 1,200 degrees Celsius. The heat radiated by this small amount of metal was enough to singe eyebrows and make woolen clothes smoke. As they tilted the pot, a stream of golden and viscous liquid trickled into the feeder channel of the mold, plunging into the darkness of the sand to find the cold chain waiting inside. This was the fire wedding, the brutal encounter between the molten cast iron and the solid forged iron of the EI chain. The risk was catastrophic due to thermal shock. If the chain was damp, too cold, or rusty, the sudden contact with the liquid metal would cause an instant vaporization of the water or oxides. The steam expands 1,600 times in volume in a fraction of a second, which would result in a volcanic explosion, launching jets of molten iron back into the workers' faces, blinding or permanently disfiguring them. Therefore, the chains were often preheated or coated with protective pastes to minimize the shock, but fear was always in the sultry air. As the iron filled the cavities, it enveloped the deformed ends of the forged iron chain. There was no actual chemical welding between the two different metals. What happened was a mechanical encapsulation. The liquid iron flowed around the hooks and knots of the chain, burying them in the center of the sphere. Gases escaped through the sand vents with sharp whistles and ghostly blue flames, signaling that the mold was full. The master foundryman observed the rise of the metal in the entrance channel, stopping the flow at the exact second to avoid waste, leaving the steaming mold on the dirt floor to begin its slow and torturous transformation. The manual labor ceased, but physics continued to work invisibly within the sandboxes. The cooling process was where the true magic of the union happened, governed by the relentless laws of thermodynamics. As the molten iron transitioned from a liquid state to a solid state, it underwent significant contraction, shrinking in size. This shrinkage was key to the integrity of the weapon. The cast iron sphere, by decreasing in volume, tightened fiercely against the end of the forged iron chain that was at its core. It was a crushing embrace, a deadly grip that would ensure that the chain would never come loose, no matter what centrifugal force it suffered during flight. However, this cooling needed to be slow and uniform. If the outer part of the ball cooled too quickly in contact with the cold air of the English night, it would form a hard shell while the interior was still mushy and warm. This would create massive internal stresses that could cause the cannonball to crack or even explode spontaneously days later, like defective tempered glass. The foundry became a minefield of popping pieces, where the sound of a sharp metallic tick meant that hours of work had been lost, and that the piece would have to be broken and melted down again. For hours and sometimes days, the molds remained untouched, radiating heat waves that distorted vision. No one dared to open the box prematurely. The forged iron of the chain and the molten iron of the ball had different rates of expansion and contraction, and removing them from the thermal insulation of the sand too soon would cause a shock that would separate the two materials, leaving the chain loose inside the ball. It was a game of patience in an environment where haste was the norm, requiring the foreman to watch so that no anxious worker tried to speed up the process by throwing water on the molds, a rookie mistake that would destroy the crystalline structure of the metal. When the molds finally cooled enough for human touch, the foundry floor transformed into a scene of controlled destruction. Men armed with heavy hammers attacked the wooden boxes, shattering the sand, hardened by heat, with violent and rhythmic blows. A suffocating cloud of black dust and silica rose into the air, covering the sweating skin of the workers with a dark, sandy paste, while the piece of artillery emerged from its earthen cocoon. What emerged was not a polished and shiny weapon, but a gray object, rough and covered with crusts of burnt sand, with the chain bent and rigid, caught between the two spheres like an umbilical cord of solidified metal. The work, however, was far from over, as the casting process left dangerous scars on the metal. At the line where the two halves of the sand mold met, the molten iron always leaked a little, creating a thin and sharp crest of metal called a burr. If a gunner grabbed this ball in the rush of battle, this shard of iron could slice his hand to the bone, incapacitating an essential man in the garrison. Worse still, these projections increased the diameter of the ball, which could cause it to get stuck inside the cannon, turning the piece of artillery into a bomb that would explode on the deck of the British ship itself. Enter the burr removers, the most undervalued workers in the chain, sitting on low benches surrounded by piles of metal. With steel chisels and coarse files, they spent hours striking and scraping the excess iron in a strident noise of metal against metal that made teeth vibrate. Sparks flew with every hit of the chisel, and sharp pieces of iron sprang like shrapnel, often blinding those who were not fortunate enough to blink at the right moment. Only when the sphere was perfectly smooth and the chain checked for flexibility did the piece receive the crown stamp of approval, ready to leave the hell of the foundry and face the sea. Transporting these monstrosities required a logistical effort that challenged the precarious infrastructure of the 18th century. Each set of chain shot weighed as much as a large child, but it was dense, inert, and difficult to stack. Ox-drawn carts with axles creaking under the weight of tons of iron bogged down on the muddy roads that connected the foundries to the shipyards. The iron, although it seemed indestructible, had a relentless natural enemy: the sea spray. Even before reaching the ships, the salty air humidity began to attack the bare metal, creating a layer of rust that could weaken the links of the forged chain, the weakest point of the structure. To combat corrosion, the balls and chains were often dipped in hot tar baths or bituminous varnish, a process that added a pungent chemical smell to the naval deposits. This black, sticky coating served as a protective skin, ensuring that the chain joint did not fuse into a solid block of iron oxide during the months of storage in the damp hold of a frigate. The Navy's purveyors were obsessive about this. A rusty chain could snap on firing, and faulty ammunition was money thrown to the sea in a wartime economy where every shilling counted. In the lower deck of the line ships, storing these pieces required military discipline. Unlike the round bullets that could be stacked in pyramids, the chain shot was unstable and needed to be stored in specific compartments or tied down to prevent the roll of the sea from turning the balls into loose projectiles that would crush the crew's feet and legs. There, in the darkness, smelling of tar and gunpowder, the engineering of the foundry lay dormant, a promise of latent violence ready to be awakened by the spark of a fuse, carrying with it the sweat and blood of the men who forged it on solid ground. The moment of truth arrived, with the deafening roar of a 12-pound cannon. Inside the dark barrel, the explosion of gunpowder pushed the two balls simultaneously, but the terrifying magic occurred the moment they left the mouth of the weapon. As they encountered the resistance of the air, the microscopic imperfections in weight and aerodynamics caused the balls to drift apart. The chain, which traveled doubled in compact, stretched violently in a fraction of a second, transforming the projectile into a deadly spinning metal dumbbell, buzzing through the smoke of battle like an invisible scythe. The physics of impact was devastating. When this spinning mass struck the rigging of a French or Spanish ship, it did not merely pierce, it grabbed and tore. The chain wrapped around stays, shrouds, and thick ropes, and the inertia of the iron balls at the ends continued the motion, acting as brutal levers that snapped thick ropes as if they were hairs. Entire sails collapsed, covering the enemy cannons and blinding. The gunners, while wooden beams weighing tons fell from the skies, crushing everything they encountered on the deck below. It was the triumph of metallurgy over carpentry, of raw industry over the art of navigation. A ship that, minutes before, was an agile and dangerous war machine, became an inert wooden bathtub, rocking helplessly in the waves. As the enemy carpenters ran desperately with axes to cut the wreckage and clear the deck, the British crew could maneuver to the ideal position for annihilation, proving that the battle was not won solely by the courage of the sailors, but by the scorching heat, the black sand, and the exhausting work of those who forged the chain in the industrial belly of England. The impact was devastating and the technology merciless. But our work of historical excavation does not stop here. Sign up now to not miss the next shipment. And tell us in the comments, what was the most brutal part of this process for you? The heat of the foundry or the physics of impact? I am curious to know what you can endure. Until next time.